Classes in Statistical Mechanics, and today a lecture by Professor George Phillies based on his books Phenomenology of Polymer Solution Dynamics, Cambridge University Press, 2011, and Elementary Lectures in Statistical Mechanics, Springer Verlag, 2000. Experimental Methods in Statistical Mechanics. Here I consider an outline of today's lecture. The primary focus of the lecture will be on the dynamics of solutions, notably complex fluids and polymer solutions. I won't say a great deal about equilibrium methods. Specific heats have played a major role in our discussion and our explanation of what was going on, and in the list of things that we can calculate with statistical mechanics. But specific heats of complex fluids are not central to the discussion I'm going to give, which is concerned with how the complex fluids move. There are a whole bunch of experimental techniques. They could rationally be discussed in almost any order. The order I choose here happens to follow the order in my book, Phenomenology of Polymer Solution Dynamics. As a result, we'll first discuss some very classical techniques, namely sedimentation, how fast things precipitate when you put solution into the centrifuge, and electrophoresis. Electrophoresis is rather like sedimentation in the sense that there is an applied external force. However, in the electrophoresis case, the applied external force is electrical, period. I'll then turn to discuss scattering, correlation spectroscopy, and diffusion. These topics are somewhat intermixed. The parts that one discusses on one transfer rather rapidly over to the other two. We'll take a piece to look at measurements that let you see how small molecules move. There are some spectroscopic techniques, there are some clever scattering methods, and then there's dielectric relaxation, a single physical technique that gives a wide variety of different numbers about the same solution. Finally, we'll turn to driven motion, that is, what happens to a liquid when you apply forces of some sort to it. In particular, we'll discuss viscosity, we'll discuss viscoelasticity and other non-trivial effects like shear thinning, and finally we'll say a bit about nonlinear effects, behavior that is certainly outside the linear regime. Throughout, the focus will be on experimental techniques and what sort of information they have given us about complex fluids. So here we are with a discussion of sedimentation and electrophoresis. If I'd been able to deliver this live, it would have been a chalk talk. I don't have a chalkboard here, so we'll just have to make do with technical substitutes. Electrophoresis and sedimentation are classical techniques for the study of macromolecules and other solutions. Sedimentation played an important role very early on in the understanding of proteins. Namely, it was through the study of proteins with the analytic ultracentrifuge that it was demonstrated that proteins were chemical compounds with distinct molecular weights as opposed to being association call weights. Electrophoresis, well, the first experiments in electrophoresis are conductivity measurements, and those go back more than a century. Let us consider physically how the techniques work. So we have, on the left, a rotating object, and we fix a centrifuge cell to the side, and there's a whole bunch of iron gummery to keep the cell from exploding, and we spin the system in a circle. A typical macromolecule, that's the black dot in the middle of the tube, is now accelerating, because it's running in a circle, in towards the middle with an acceleration magnitude omega square r. So far as the object is concerned, it cannot tell the difference between the acceleration and being subject to a gravitational field. In either case, we get sedimentation. Things fall out of solution. or in the case of cream and unhomogenized milk, they float to the top. There are then a series of different interesting experiments you could do to study dynamics under different conditions. First, and most traditional, you can take a dilute solution of macromolecules or whatever and spin it up, and then two sorts of things happen. The first thing that happens is that if you have a macromolecule, here's a macromolecule, and the macromolecule is floating at some height and is heavier than water, or denser than water, we should say, it will sink to the bottom. And the sinkage rate is determined by its buoyant mass and its drag coefficient. On the other hand, if you keep spinning, you eventually get some sort of a layering effect at the bottom, and the concentration of macromolecules as a function of height is described by the barometer equation. It's the same equation that describes air pressure versus altitude, except that the scale height here is a little less than 15,000 feet. A second experiment you can do, these were only done more recently, is to say, well, we'll take the same solution of polymers or whatever, and instead of studying dilute objects that don't interact with each other, we'll study a concentrated solution where there are lots of interactions, and we will again ask how the rate at which things sediment depends on the concentration, the molecular weight for polyelectrolytes, the pH, the salt concentration, and other standard variables. The third experiment you could try, and the first of these go back to about 1960, is to say I have a polymer solution, the black lines, and I have dropped into the polymer solution some sort of a probe molecule. If I'm clever, I rig the solution so that the polymers are more or less invisible and are fairly uniform in concentration and are sufficiently density matched that they just sit there, and I observe the sedimentation of the probe object through the polymers. This gives me information of yet a different sort on the properties of the polymers in solution. Let us also consider, right side of the slide, electrophoresis. The general notion is that if you have a solution, and the solution is sitting there, you apply an electric field, and as you have applied the electric field, things migrate. Now, saying you apply the electric field is a bit more complicated than it sounds. Namely, you are applying an electric field inside a conducting liquid, and you have to do clever things at the end, or, gee, after very little time, there's no current. So we have an applied electric field. We have objects moving. This technique was used, 80 years ago to separate, for example, different sorts of proteins. If you try applying this technique to DNA fragments, you have a little problem. In plain solvent, the DNA fragments decline to separate. One solution is to replace the innards of this capillary is filled with water. We'll say we'll replace this and we'll fill the innards of the capillary with cross-linked gel. Or we'll just use the cross-linked gel itself as a separatory matrix. And that actually works, except making really uniform gels turns out to be experimentally tricky. There is, however, a third solution. There are several others. And the third solution say, well, we'll take just electrophoresis in a solution in a liquid, and we will dump stuff into the liquid. We will dump stuff like polymer molecules, micelles, all sorts of things we could imagine dumping into the liquid. And the stuff we've dumped into the liquid, the black squiggly lines, have the important feature that they are electrically neutral. They just sit there during the electrophoresis process. In principle, they don't have to be neutral, but let's try to keep things simple for a moment. We now apply an electric field, and we discover that if these are DNA fragments, I'll explain in a moment why they're appealing. The DNA fragments of different size electrophoresis down the tube at different speeds, and you can separate them. And you can use this separation as a basis for doing DNA sequencing. I refer you to the biology literature for that. However, there's something else you can do with these, which was rather less well understood for a long time, or at least it wasn't thought about because it wasn't what good electrophoresis scientists were interested in. Namely, instead of saying we are using this to study separation and how to get better separations, we can say we have a DNA ladder, or RNA ladder. We have a string of single or double-stranded, polynucleotides of different length. The molecular weights of these things are known with incredible accuracy, and so we produce a species, and they are all the same and differ from each other markedly. And so we can fire this whole bunch of probes down the solution, the red and green dots, and we can observe how the stuff in the solution of the neutral polymer slows down the red and green dots. Gee, we are now studying the dynamics of the neutral polymers, things that do not move when an electric field is applied, not directly, but by observing the electrophoretic motion of probes through them. So there we see sedimentation and electrophoresis, very old techniques that have been brought to new uses. Here I consider an outline of today's lecture. The primary focus of the lecture will be on the dynamics of solutions, notably complex fluids and polymer solutions. I won't say a great deal about equilibrium methods. Specific heats have played a major role in our discussion and our explanation of what was going on, and in the list of things that we can calculate with statistical mechanics. But specific heats of complex fluids are not central to the discussion I'm going to give, which is concerned with how the complex fluids move. There are a whole bunch of experimental techniques. They could rationally be discussed in almost any order. The order I choose here happens to follow the order in my book, Phenomenology of Polymer Solution Dynamics. As a result, we'll first discuss some very classical techniques, namely sedimentation, how fast things precipitate when you put a solution into the centrifuge, and electrophoresis. Electrophoresis is rather like sedimentation in the sense that there is an applied external force. However, in the electrophoresis case, the applied external force is electrical, period. I'll then turn to discuss scattering, correlation spectroscopy, and diffusion. These topics are somewhat intermixed. The parts that one discusses on one transfer rather rapidly over to the other two. We'll take a piece to look at measurements that let you see how small molecules move. There are some spectroscopic techniques, there are some clever scattering methods, and then there's dielectric relaxation, a single physical technique that gives a wide variety of different numbers about the same solution. Finally, we'll turn to driven motion, that is, what happens to a liquid when you apply forces of some sort to it. In particular, we'll discuss viscosity, we'll discuss viscoelasticity and other non-trivial effects like shear thinning. And finally, we'll say a bit about nonlinear effects, behavior that is certainly outside the linear regime. Throughout, the focus will be on experimental techniques and what sort of information they have given us about complex fluids. We now turn to scattering techniques. The key underlying basis of scattering techniques should be recognized by physicists because it's the same as the first order Born approximation. If you're a chemist, that's less familiar, so I'll try to explain what's going on. Over here at the left of the screen, we have a laser or a neutron generator or something, which is giving us a beam of light or neutrons or whatever, which proceed along in the direction labeled by k sub I. K is the wave vector. The magnitude of k is 2 pi over lambda, lambda being the wavelength. Those of you who are accustomed to infrared and Raman spectroscopy should know this is the physics wave vector, and you are used to the chemistry wave vector, 1 over lambda. In any event, the waves chug along from left to right across the screen and eventually encounter particles, the little black circles. They're actually scattered in all directions, but we'll only talk about scattering in one direction at a time. So you need some clever arrangement. A pair of pinholes is actually the best choice. Pinholes being perfect collectors. Over here, the light is collected and has come off in some one direction. The scattered light also has a wave vector. Its wave vector is k sub f. We'll choose one particle as being at the origin. That's the one in the lower left. The scattered wave chugs along, follows the indicated path. When it gets to the detector, which is off near 002 here, when it gets to the detector, it is taken as having phase shift of 0. Now suppose the light instead follows the upper of the two paths to the other particle, and then follows the rightmost of the two paths to the detector. Its path length is longer on one arm, namely, it has to advance a further distance parallel to ki, and then it's shorter on the other arm because it doesn't have to move as far along the k sub f direction. The net result of this is that there are a couple of phase shifts. And the phase shifts, it's a wave. We have the wave vector. We have a distance traveled. The particles have positions labeled by r vector I. And so this phase shift is minus ki dot ri, minus because it's longer. And this phase shift is plus kf dot I ri, plus because the path is shorter. The net result is that the scattered field is determined, well, E sub s is equal to E0. E0 is a bunch of constants that are determined by how good these things are at scattering light and how much incident light there is. And then each scattering from each particle has a phase that is determined by the particle's position. And the phase, expressed as a difference relative to this first particle at the origin, is I, kf minus ki, dot r sub I. We define k sub f minus k sub I, the change in the wave vector due to scattering, as q, the scattering vector. The scattering we'll be talking about is called quasi-elastic. That is, the photons are scattered, but they are scattered almost exactly without change in energy. And as a result, the magnitudes of k sub I and k sub f are exactly equal to each other, and q is determined by the wavelength of either of them, and by the scattering angle, the angle giving the change in the direction of light. The final detected light is shown by the bottom equation. The electric field at the time t is a bunch of constants which I've represented by E0, and then we add up the phases due to scattering from each particle, because each particle scatters light which, when it reaches the detector, has a slightly different phase. And the phase difference is the dot product of the scattering vector q with the position r of the particle at time t. We now advance to discuss additional issues with scattering. First of all, the scattered field is ak of t, or proportional to it, and that's a sum over the positions j equals 1 to n of all of the particles of this phase factor e to the I q dot r. One thing we can certainly do is take the ensemble average of two of these. That's the next line. It's labeled static scattering, and it's a product of a sub k and a sub minus k. The exercises in the chapter on spatial invariance will show that if you wrote it as a sub k, a times a sub plus k, the ensemble average would be 0, but fortunately that's not what we have experimentally. That's determined by a double sum. The summation variables are j and m over the number of particles. J and m go independently from 1 to capital N, and what we add up, since there are two factors, e to the I q dot r, or rather e to the I k dot r, and the signs on k are opposite, is this object labeled static structure factor. If you run that through the ensemble average as indicated, do the calculation right, you discover that what you are getting out is, with wave vector q, the spatial Fourier transform of the radial distribution function. And indeed, static scattering is how you measure radial distribution functions. It's also how you do X-ray crystallography. What you do is you measure scattering intensity versus angle. There's only one angle there if you're doing the scattering from a liquid. If you're doing scattering from a crystal, life is much more complicated. We won't talk about that. The other choice, though, is to do what is known as dynamic or quasi-elastic scattering. In both cases, the scattered object could be all sorts of different things. I primarily myself talk about scattering of light. However, you can also do scattering of X-rays. Its formulas are exactly the same. You can do scattering of neutrons. There is a modest trick with neutrons that what you readily measure is slightly different. Nonetheless, we're doing dynamic scattering, meaning we're comparing a sub k at one time and a sub minus k at a second time. I'm being a little inconsistent whether I'm calling the scattering vector k or q, but in this equation it's k throughout. And a sub k of t times a sub minus k of t plus tau is this double sum over j and m, where the phase factors show where the particles are at 2 times. Now, what does that object mean when we take its ensemble average? Well, a sub k of t is 0 if the solution is absolutely uniform. If there are fluctuations with position and the concentration of particles, a sub k of t is not 0. And what the dynamic scattering tells you once you take the ensemble average is, well, suppose we start out with a concentration fluctuation. What our detector sees is a single spatial Fourier component of the concentration fluctuation across the whole system. And what the ensemble average tells us is what happens on the average as time goes on. So we start out with a concentration fluctuation at time t, and by the time we get to time t plus t tau, on the average the fluctuation has tended to relax. That's what our dynamic scattering does. Now, the relaxations are in solution are due to diffusion, and before I can talk about that some more, I have to say something about how diffusion works. A few words about diffusion. We go back to the 19th century, and Brown observed, you look in through a microscope at a dilute solution of pollen, and the particles jitter about. At about the same time, Fick explained how diffusion works, namely, if you have a concentration gradient, the particles, molecules in the gradient diffuse down the gradient, the concentration gradient goes away. He explained this by analogy with Fourier's theory of the diffusion of heat. We skip ahead to the start of the 20th century, and Einstein and Langevin give an explanation for diffusion. Einstein gives the diffusion equation, d equals kT over f. Langevin explains at long times that could be observed at the start of the 20th century, that the mean square displacement of one of those moving particles goes as 2d times the time t, and suddenly once you had something to do with all of the measurements on diffusion, you could confirm that the Langevin model was correct and understand what you were looking at. This is a picture for a dilute molecule. Of somewhat more interest is what happens when the molecules are not dilute. When the molecules are not dilute, they interact with each other, and there are 2 sorts of things you can measure. One is what is described as mutual diffusion, which describes the diffusion of particles down a concentration gradient. And the notion in mutual diffusion is that we have a cluster of particles here, we have fewer particles to the right, There's current J of the diffusion. The current J is partly due to the random walk of the particles, and partly due to the fact that the particles interact with each other, and in the case where I'm drawing things, repel each other and push each other down the gradient. The diffusion coefficient is also described as the pair diffusion coefficient because it includes a description of the relative motion of two particles. There is, however, another way to do a diffusion measurement. On the right, we have a solution of polymer chains, and we have cleverly reached in and painted one of the chains green. Now you may say, that's a little challenging, isn't it? And the answer is you attach to the polymer molecule a fluorescent dye tag like fluorescein, and when you illuminate the solution, you can see where the fluorescein molecules are. You measure the diffusion of the fluorescein tagged molecules through this uniform background of untagged molecules, and you are now studying tracer diffusion, also known as the self-diffusion coefficient. Alternatively, you take the polymer solution and you drop into it. The red sphere is simply a suggestive example, a probe particle or a probe molecule, which is very different from the polymer chains, and you measure the diffusion of the probe particles through the background solution. This is probe diffusion. So if you look hard at this, we really sort of have, in addition to dilute solution diffusion, in non-dilute solution we have mutual diffusion, which we can measure. That's what quasi-elastic light scattering measures, the mutual diffusion coefficient. We also have tracer and probe diffusion. Now you can use quasi-elastic scattering to measure the probe diffusion coefficient. What you do is to choose a background, a matrix polymer, that is isorefractive with solvent, so it scatters more or less no light. And you choose a probe polymer or a probe particle whose index of refraction is very different from that of the solvent, so that it scatters a great deal of light. And then, though you have to be careful at the edges, you can measure the diffusion of the isolated tracer or probe particle through the perhaps quite concentrated polymeric matrix. I will note that when I came onto the scene in 1969, the image that was used for diffusion was always the Langevin diffusion. The number that you measured with the diffusion measurement was called the diffusion constant, at least in light scattering circles. Some chemists knew better. And there was no recognition that there were two different diffusion coefficients, let alone that it was intelligent to ask which diffusion coefficient light scattering spectroscopy measures. The answer is indubitably that light scattering spectroscopy measures the mutual diffusion coefficient in a binary system. Unless you're being very clever with your probe system, in which case you can in principle use light scattering spectroscopy to measure a tracer diffusion coefficient. In dilute solution, there is a straightforward interpretation of the object you measure using quasi-elastic scattering. That's this thing, sometimes known as the intermediate scattering function or the dynamic structure factor. And the answer is there's a distribution for probability of the displacement delta x of each particle, and G1 of Qt measures the spatial Fourier transform G. That's actually a correct equation if you're talking about pulsed field gradient NMR, but we aren't. In concentrated solution, if you're doing quasi-elastic scattering, there are actually two correlation functions you have to include, one of which is simply the likelihood that a particle will displace by delta x during some time, which we could call t or tau, and the other is the probability of that displacement given that there's a second particle located at some location 2. So R12 is the separation factor. Except in very dilute solution in simple fluids, P delta x of t is quite complicated. You will sometimes see people claiming that you can write the dynamic structure factor. This is what light scattering spectroscopy would measure, or what pulsed field gradient NMR would measure, as e to the minus q squared delta x squared over 2. That would be correct if P of delta X and T is Gaussian, but that's completely false in complex fluids. This equation is totally wrong, except in this very special case of extreme dilution. Unfortunately, as a historical matter, there's a wonderful book on light scattering and spectroscopy by Byrne and Pecora. And Byrne and Pecora talked about the issue that was au courant at the time, which was basically measuring diffusion coefficient of very dilute particles as a way to determine their size and molecular weight. At very high dilution, the equation, which I've carefully crossed out, is actually correct in most reasonable cases. Well, not if the particles are heavily charged and there's really no salt in solution. And the net result is that this equation, which was intended only for a special case, it was perfectly obvious to anyone who read the book when it came out, as I did, well, except in this very special case, this equation is entirely erroneous, and correspondingly the claim that you can use quasi-elastic light scattering or several other techniques to measure the mean square particle displacement, which of course is going to be time dependent, is also totally wrong. Oh yes, T and tau in this first line are interchanged once. Sorry about that. However, this is a chalk talk, except I can't simply go in with my thumb and erase things. So there's this diffusion interpretation, which is actually quite complicated. We now come to technical methods for measuring small molecule motion. There are actually a fair number of them. They're described in my Polymer book. However, starting from the simplest upper right-hand corner, conductivity, we have a solution with charged small molecules, for example, ions in it. We apply an electric field. Again, you have to be clever and know how to do that inside the solution. You need electrochemical activity at the two ends, not just an applied electric field outside. And the current J is proportional to the electric field. It's proportional to the concentration N of the charged objects, and it's proportional to the conductivity lambda. And if you drop into solution things that raise the viscosity or whatever, you can see how lambda depends on solution properties. We now come to two slightly more simple-minded or straightforward scattering methods. One method is fluorescence photobleaching recovery, FPR, also known as fluorescence recovery after photobleaching, or FRAP. The notion in FPR is that we have an initially uniform solution. We have tagged some or all of the molecules with a dye. The dye is fluorescent, so when we illuminate, we can see where the molecules are, or at least where the concentrations are. We now blast the solution with a high-power laser beam, and the high-power laser beam bleaches the dye in some areas. A standard pattern of bleaching is stripes. And so the solid circles are molecules that are currently not bleached, and the round open circles, the dashed circles, are molecules that are bleached. We now sit and measure, and what happens as time goes on is that the bleached and unbleached molecules switch places, and as they do, this concentration grading, fluorescent and not fluorescent, gradually goes away. This is not a fluctuation process. This is we created a gradient. However, the method we use to create a gradient, approximately speaking, does not disturb the concentration of the molecules in the system. So as long as your dye doesn't do anything too drastic when it's bleached, like becoming heavily charged, the bleached and unbleached molecules are basically very similar to each other. And therefore, the diffusive process we are looking at is self-diffusion. We now come to the bottom of fluorescence correlation spectroscopy. We look into the solution at a very small volume of solution. And sitting in the very small volume of solution will be some number of fluorescent particles. As time goes on, the fluorescent particles diffuse in and out of the observed volume, which is being hit with the probe laser, so we either count or somehow elsewise measure the presence of the fluorescent molecules. There are fluctuations up and down in the number of molecules as the molecules diffuse in and out of the volume. This is a diffusion technique that was used by Arne Westgren 110 years ago to measure diffusion coefficients. The important issue on fluorescence correlation spectroscopy, though, is that you're actually watching equilibrium particles move. There's one more curious feature of this. We go back to the prior slide, and I commented that G, quasi-elastic scattering, measures mutual, not tracer diffusion. That theoretical result is due to me. Until I did my work, which was part of my doctoral thesis, people thought, gee, D equals KT over F, particle interactions are irrelevant. But in fact, mutual diffusion is what is measured by light scattering. Soon after the original FCS, fluorescence correlation spectroscopy papers came out, I wrote, I believe it was the first paper not written by the original creators of the technique, a paper explaining that FCS could measure both DM and DS depending on what fraction of the particles were labeled. If all of the particles were labeled, you measured the mutual diffusion coefficient. If only a few particles were labeled, you measured the self-diffusion coefficient. That prediction was actually confirmed by Skalatar much later. It's a very pretty experiment, and it shows that my predictions were correct. Yet another method of studying molecules, we're now in the lower left corner, is VH scattering, or depolarized light scattering. There's several variations on this, but the general idea is we send into the system a polarized beam of light. Some of the light is absorbed by molecules that are not regularly spherical in shape, that are optically anisotropic. And when the light comes out of the system, it comes out with a different polarization. It went in vertically polarized, and when it comes out through 90 degrees, the light, instead of being polarized perpendicular to the scattering plane, is now in the scattering plane. However, the amount of light that the molecule scatters depends on, and depolarizes, depends on its orientation with respect to the polarization vectors of the directions. And so if the molecule does rotational diffusion, which it does, the amount of light scattered by any one molecule goes up and down. Experimentally, this happens at very high frequencies. You observe the results at very high frequencies by doing what is known as Fabry-Perot interferometry. That's the dominant method used. And the light goes in at one frequency. You have to tune the laser in particular ways known as single moding. And when the light comes out, it comes out over a range of frequencies, because the frequency of oscillation or diffusion of oscillation adds into the frequency of the light. And so you get not a time domain relaxation, but a frequency domain spreading of the frequency of the light, and you can therefore infer the rotational diffusion coefficient. In complex fluids, rotational diffusion couples to damped or overdamped, well, near damped or overdamped shear modes in the liquid and other possible variables, and you can get fairly complicated VH scattering spectra as a result. We finally advance to the upper left, to pulsed field gradient NMR spectroscopy. PFG NMR, in the end, measures sort of what quasi-elastic scattering does, except on completely different length and time scales from completely different objects, and intrinsically it only measures the single particle, the self-diffusion coefficient. Let me try to explain how it works. The coordinate system with the arrow sticking up is, in point of fact, an atomic nucleus in a magnetic field that points vertically along the z-axis. Because the magnetic field points along the z-axis, the spin, the arrow, precesses around it like a gyroscope, and the component of the spin in the plane goes around in a circle at some frequency. The frequency has a value omega naught. So what we do is we line up all of the spins with the radio frequency pulse. I am skipping many, many details. We allow the spins to precess, which they do with that frequency omega 0. And then at some point, for a little while, we apply a magnetic field gradient. G is the field gradient. G times X, or perhaps we should call it Z, because usually you apply the gradient in the vertical direction. GZ is the magnetic field, the extramagnetic field at the location of the nucleus. Gamma, because we have the expression gamma GX, gamma converts the field intensity into an extra rotation rate, and this whole rotation goes on for a period delta t. We turn on the gradient, we turn off the gradient, and when the gradient is off, the spins just precess at omega naught. We then apply what is called the pi over 2 pulse, which has the effect of turning all the spins upside down. And when they are turned upside down, they look at the applied magnetic field, and instead of going around in circles one way, it's not drawn very well. This is supposed to be, the top is supposed to be a left-facing arrow. They now go around in circles in the opposite direction. So we set the spins up, and they rotate at omega naught, and after a while we flip them over, and we wait exactly the same while, and they have now come back, because they're now rotating at minus omega naught, back to their starting point. We can check to see they're all lined up. The field gradient changes that. We have one field gradient, which has the effect of, how shall we put it, giving an extra phase gamma gx delta t. And we have a second field gradient, except now the spins are upside down, which gives a change in phase minus gamma gx delta t. And if we describe this rotating object as a complex exponential with a phase e to the I integral omega t delta t, the rotation due to the background field omega naught gets canceled out. This is why it's called spin echo. However, if the nuclei are moving x to x prime, x up here, x prime down there, are not equal, and therefore there is a loss of coherence. And the loss of coherence, that is, the spins at the end don't quite line up perfectly, it has the size gamma x delta t times the displacement delta x. Well, if you call gamma x delta t, I should have called it gamma g delta t. Sorry about that. Gamma g delta t. Remember, this is a chalk lecture, not a polished slide lecture. There's a gamma g delta t equal q, and there's a displacement. And the displacement we can detect as a loss of coherence of the spin echo. And you have to calibrate it, but in fact this expression is the self-diffusion dynamic structure factor, and it's subject to all the issues I discussed on the last slide, except you are indubitably using the technique to measure self-diffusion. We now turn to dielectric spectroscopy. Dielectric spectroscopy is noteworthy for the remarkable number of different parameters that it manages to yield out of some relatively straightforward, if instrumentally clever, experiments. There are several core issues. The general notion, well, let's go back to freshman physics. In upper left corner, there's a capacitor. And you put a charge on it, plus and minus, and you measure an electric field across it, or vice versa. And the net result is that as you change the dielectric constant of the material between the plates, you change the amount of charge that can be stored for a given applied field, or vice versa. Real capacitors, as seen in instruments, are usually not parallel plates, but in fact for dielectric spectroscopy, something fairly straightforward like this is actually what is used. Something like this. And as you put different materials between the plates, you get different results. Now, one thing you can do that doesn't get talked about to freshmen is to apply an alternating voltage, so that instead of one plate always being plus and the other minus, they pop back and forth in a sinusoidal way. And there's then a question of what the response is, say what the stored charge is. And the answer is G. The response function is a function of frequency. If you change the frequency, the amount of stored charge, which of course is also oscillating at omega, changes. Furthermore, in general, epsilon is complex. That is, well, a freshman would say, gee, if you apply a voltage, there's a charge. If you turn the voltage off, there's no charge, and the two change in unison with each other. But if you actually do this experiment and apply an alternating field, there is a component of the charge that is in phase and a component of the charge that is out of phase. You can switch these things around in various ways. And the net result is that epsilon is complex. Okay, so what can you do if you want to apply dielectric spectroscopy to a complex system? I'll talk specifically about polymers. This is out of my book, but many of the issues are the same. If I have a polymer molecule and I'm clever with my organic chemistry, I can arrange things so that the polymer molecule has a dipole moment, a fixed dipole moment, that points along the molecule from one end to the other, and therefore the polymer molecule as a whole has a dipole moment. When we usually talk about dielectric response in solids, we're talking about electron clouds moving hither and thither, back and forth. When we talk about organic molecules dissolved in liquids, the dipole molecules are attached to the molecule and can only move if the molecule moves. So the frequencies at which the dipole moments can change are much lower than they would be in a solid of some sort. In any event, the mean square size of the dipole moment, that's the label P, is proportional to the mean square distance between the two ends of the chain, because the chain is simply giving you a vector sum of dipoles that point from one end to the other, and that vector sum is equal to the dipole moment P. And therefore, the dielectric relaxation on polymers lets you measure the mean square size, the end-to-end distance of a polymer chain. Second, if you line the polymer molecules up somewhat by applying an electric field and let go, there are other ways of doing the experiment. You have rotational diffusion. The chain rotates end over end. And as it rotates end over end, the end-to-end dipole P forgets which way it was originally pointing, and you get an exponential relaxation with a relaxation constant gamma. So you can measure rotational motion, rotational diffusion. If you have a solid body, well, it just has 3 rotation angles, and the dipole sort of lets you pick out one of them. If you have a polymer chain, though, the chain is rather complicated in shape and is flexible, and therefore the end-to-end vector can relax in several different ways. And so if we plot log plot epsilon versus omega, instead of seeing an exponential decay, we get something complicated, and maybe there are bumps, well, at least slower roll-offs, modes at high frequency. In any event, you can see a mode structure which gives you much more information than just a rotational diffusion coefficient. Finally, if you are a really clever organic chemist, you could do the following. Note the red and green, the Christmas-colored chain in the lower right corner. The Christmas-colored chain has been assembled of two different chemical species, one of which has dipole moments, that's the red one, and one of which has no dipole moment. The one with no dipole moment does not contribute to the dielectric relaxation, and so when we watch relaxation, we basically are watching what one end of the chain is doing by itself. Therefore, by building chains of this complicated chemical sort, what are called block copolymers, and one of the blocks is dielectrically active, we can measure polymer internal modes and tell exactly which part of the chain we're looking at when we're talking about the mode. That's actually quite radical. It's a very powerful technique which has only been lightly exploited to date. That's it for dielectric relaxation. What we see here is the last slide of the talk on viscosity and viscoelasticity. In many papers on non-dilute polymer solutions, the last, that's this, shall be first. Well, that's okay, that's a choice. But here, the last is last. What do we mean by viscosity? Well, consider the figure in the upper left corner where we have a vertical pipe and a constriction at the bottom, and a flow rate through the pipe that's inversely proportional to the viscosity, the resistance to pouring of the liquid. The pipe can have a more complicated shape. Instead of having liquid flow out the bottom, we can take a marble, drop the marble into the pipe, and time the fall of the marble down the pipe. Gee, guess what? You're still timing a flow rate. There are various complications, whether you're using a capillary viscometer, that's the little constriction, or a falling ball viscometer, but you're still measuring a linear flow rate. An alternative to this is to take two plates. Shown here is two parallel plates moving at V in the two opposite directions. In order to get the plates to move, you have to apply a force per unit area to the system, which is proportional to the velocity difference. It's also inversely proportional to the distance between the plates, and it's proportional to the viscosity. The larger the viscosity, the more force you need. Now, if you actually want to do this and have a nice clean measurement, well, first of all, you use circular plates and you rotate one of them. And maybe you have two concentric cylinders and you rotate the one or the other. And perhaps one of the plates is flat and the other is an upside-down cone contacting the stationary flat plate in the middle, and you rotate the cone back and forth. But in any event, you have two plates inducing a flow and you measure the force. Now, having said you're going to do this experiment, there are now, particularly with the cone and plate, there's some cute add-on experiments. For example, you could say, instead of the cone-shaped thing or the flat plate rotating in a circle at constant speed, you could say we will have it oscillate back and forth through some angle. And I did say some angle. The angle is typically not too large, and we have some frequency. And corresponding to that frequency, well, we have a velocity, which is at some frequency, and we get a force, which is at the same frequency, and corresponding to that, we might have said, well, we have a frequency-dependent viscosity. We actually, note the arrow crossing out the eta of omega, say we have a storage modulus and a loss modulus, a G prime and a G double prime, which are functions of frequency. The reason we have both of these is that if the plate is oscillating at some frequency, the force that shows up has a component that's in phase with the oscillation motions, and it has a component that's 90 degrees out of phase with the oscillation motions. And so we actually have two components. If this sounds like dielectric relaxation, that's because mathematically it's very much like dielectric relaxation. Well, what happens if you measure, say, the loss modulus as a function of frequency? The answer, and I have plotted it not the way many people do, but as G double prime over omega, is that low frequency G double prime is flat. And then with increasing frequency, it falls off as, good heavens, it's another stretched exponential. And then at higher frequencies, there's a crossover to a power law fall-off with frequency. And at still higher frequencies, you sometimes get additional bumps, additional modes, just as you did with dielectric relaxation. The statement that you have G double prime and omega, and you get this frequency dependence, there's another way to do things, which is to take our gadget here, or this gadget, and increase the shear rate, the delta V, delta L between the two plates. And as you increase the shear rate, you get a phenomenon known as shear thinning. Shear thinning has the feature that as you increase the shear rate, apparent viscosity becomes less, and the curve, except that it's a function of shear rate rather than frequency, looks exactly like the curve I'm giving you for G double prime over omega. In fact, the two curves pretty much, though perhaps not perfectly, lie on top of each other. Some sources will say that this is very hard to explain. Now, having said you have viscosity, one thing you can do is to change the liquid you're studying. And if you do that, well, one choice is to plot log of viscosity versus log of concentration, and you discover that viscosity climbs very rapidly with increasing concentration. In fact, it increases a stretched exponential in concentration. I'm showing one of those. In some systems, you see a rollover to a power law concentration dependence at larger viscosities. In other systems, you don't seem to. So the viscosity can depend on concentration. Now, if you're ingenious, there's another type of viscosity completely which often doesn't get covered, which shows up because if you have a polymer melt or a very concentrated solution, you can pull the melt out into fine threads. If you have ever seen, well, I guess the most familiar example is cheese in a pizza, and you pull up the cheese in the pizza, and it's at the right temperature, the end of the thread extends and extends, and you have these very fine pieces of cheese linked between the piece on your fork and the big pizza on the plate. This is very annoying. This is known as thread drawing, so to speak, and the resistance to pull is called extensional viscosity. Extensional viscosity is very hard to measure accurately. For one thing, if you extend, in order to have constant extensional rate of change of extension, your velocity of the pulling object has to increase very dramatically with time, and this gets ugly. In addition, there are hazards where, to some extent, there are assertions that the threads tend to become unstable and develop little dimples, and all of the stretching occurs in the little dimples, and gee, it's not a simple system anymore now, is it? There are other ways you can do things that are nonlinear. If you are pushing a solution through a pipe, you can crank up the pressure and measure viscosity versus flow rate. That's shear thinning. If you come back to the upper right, we had the two parallel plates, or better yet, the plate, the flat plate, and the cone touching it only at its tip. Now, usually what you do if you're rotating the cone or the plate back and forth is that you rotate things through a small angle, but you can also do what is known as large angle oscillatory studies, and in the large angle oscillatory studies, you, oh, surprise of surprises, make the angle large and watch what happens to the viscosity. There are a couple of other variations on large angle. For example, suppose we are doing oscillation at some frequency. If the system is nonlinear, you might say, well, it's a nonlinear system, you're driving it at some frequency, you should see overtones or, God help us, undertones. You could. And if you see overtones or undertones in the developed force, that's a nonlinear effect. Well, in order to do that, what you need is modern computational techniques where you measure the position versus time of the cone very accurately, and the applied force versus time very accurately, and then you do Fourier analysis and look for frequency overtones, and you find them. It's a nonlinear system. It's sort of like nonlinear optics, except in math, but the details are very different. All right, we have now covered a whole bunch of different techniques, all of which qualify as experimental statistical mechanics. We can do experiments using very different sorts of systems and machines to measure all sorts of quantities, some of which can even be represented as correlation functions, many of which, in fact, can be represented that way. I've talked mostly about polymer solutions because that's what I do research on. It turns out that if you have micelles soaps, there are certain combinations of charged and non-charged molecules that give you micelles. Instead of being little soap bubbles in solutions, they're huge long threads that behave a lot like polymer chains, except they can go straight through each other because they're not covalently bonded. If you look at my book, you will discover I did something else. I give you a whole chapter on colloid dynamics. The reason I did that is that colloids have between them more or less all of the same forces that polymer chains do. They can't go through each other. They could, I guess, be charged. They have hydrodynamic interactions, that is, one object moves, creates a weight, drags other objects along. But they're spheres. Colloidal spheres are spheres. They're not long chains. They can't tie each other in knots. And it is interesting to compare colloid and polymer dynamics, which have many great similarities to each other, which says something about the importance of the forces and the relative importance of the shapes. However, we now conclude this broadcast of the Phillies Emergency Teaching Network, a broadcast offered because when I walked out my door this morning, I did not even get to the third step on my stairs before I had an interesting slide and ended up sitting down. Fortunately, I was wearing a down coat and I'm well padded, but nonetheless, I didn't even try to come into work to give this lecture. And with that, since I am lecturing on December 9th, 2014, Merry Christmas and Happy New Year to everyone.